St. Petersburg in Russia. Right here in the city centre, scientists at the Vavilov Institute are safeguarding a very special treasure, the so-called Vavilov collection. The Vavilov collection is a collection of agricultural plants and crops, one of the largest worldwide, and maybe the most important of its kind. The collection is the outcome of a series of expeditions undertaken by Nikolai Vavilov, a famous botanist in the early 20th century. Vavilov traveled the world with a clear goal. As a Soviet botanist, his main focus was on crop diversity. He wanted to have as many varieties possible in order to develop new, improved crops and therefore help secure food supply for the Soviet Union. By collecting many varieties, Vavilov could trace back most of today's crops to the so-called centers of origin, places where the natural ancestors of our present agricultural plants can be found up until today. Being a scientist, not a politician, Vavilov preferred the ideas of Charles Darwin over socialist botanist theories, a preference that landed him in prison where he died in 1943. Nevertheless, his collection survived, was preserved during the Second World War, and is utilized to this day by botanists and seed developers around the globe. In order to keep the seeds germinable, some of them have to be frozen at very low temperatures, while others need to be replanted from time to time. Thanks to Russia's extensive landmass, Vavilov was able to establish subsidiaries of his institute covering the climate zones necessary to regrow his accessions. The Pavlovsk experimental station on the outskirts of St. Petersburg is one of the places where some of these accessions are grown. Filled into special bags and deep frozen, the selected berries will be ready for shipping to the project partners. Dundee in Scotland. Here at the James Hutton Institute, Derek Stewart is busy with a lot of berries he receives from partners around the world. Derek's institute has a central function within the Bachbury project. Today, Alexandra Foyto is going to analyze the chemistry in one of the berry samples they received. In order to execute the analysis, the berries have to be processed into a liquid state. This so-called extraction procedure is carried out in a standardized way for each berry. This makes it possible to compare the chemical compositions at a later stage. The different molecules of the berry are detected by the use of heavy machinery. Each peak represents the mass of a molecule that was detected. To find out which molecule it really is can be a puzzling job. Claudia Nunes works at EBET, a research facility near Lisbon, Portugal. Her research is dedicated to mental health. Therefore, berries could play an important role, as Claudia receives promising extracts from Derek's lab in Dundee. It is assumed that the polyphenols from berries could positively influence Parkinson's disease. The phenolic compounds are tested on yeast, but not an ordinary one. It's a genetically engineered yeast that suffers from Parkinson's disease just like a human brain would. Therefore, it is called humanized yeast. By producing the proteins that trigger the disease, the yeast itself is of a self-destructive nature. If the berry extract can prevent the protein from killing the yeast, it may also save our brain cells from the same protein. Different growth curves, therefore, prove the efficacy of a substance. Understanding the way the compounds within the berry extract prevent the Parkinson's disease proteins from destroying cells is the precondition for developing a drug. In any case, yeast would be just the first step on a long journey. For a long time, berries have been known for their viability as a food colorant. This lab in Montpellier, France, is specialized in the development of natural food colorants, a highly demanded product in today's food and beverage industry. Finding a color pigment within a plant does not automatically mean it can be used. There are many requirements a pigment has to fulfill in order to be used in industry. An essential property is the availability of the pigment in large amounts and a constant stable supply. This is where the concept of Bachberry could make a difference. Producing natural colorants in a bacteria can guarantee a constant, stable harvest and therefore unlimited scalability and supply. Testing the pigment as colorant for beverages starts with a standardized beverage. The Bachberry pigment is mixed with the liquid, making it comparable to other already existing colorants. For the industry, it is important that a pigment is able to withstand the harsh conditions of transport and shelf life. A professional pigment has to be tough. After testing, the colorants are compared. That comparison needs something more precise than a human eye, the color meter. It is able to detect even the smallest differences and give them numeric values. If a pigment is detected that meets the needs of food production, it is still a long way to bring it to the market, especially when berry extracts are no longer produced by berries. Nuno Faria from Biotempo in Braga, Portugal is engaged in industrial fermentation. Nuno takes part in the Bachberry project for a good reason. When it comes to the production of chemical compounds, bacteria in a fermenter have big advantages over plants. Moreover, fermentation can happen anywhere. Once the genetic information is transferred from the berries into producer bacteria, the Bachberry compounds can be produced independently, saving arable land for food production. As other project partners were able to engineer the polyphenol-producing bacteria, it's up to Nuno to raise them well. As testing compounds from berries, engineering bacteria and experiments on fermentation are continuing, Bachberry already achieved an important goal.